Okay, hi everyone. Welcome to session 3 of Intro to CP. Me and the other officers are really glad that you came here today. My name's Sarthak and I'll be leading the session along with Tony. And today we'll be talking about arrays. And make sure to follow along on the slides. The link is tinyurl intro CP3 slides. So before we begin today, you should know that the ACM internship application is live and that it will be due tomorrow at midnight. And the internship is a great way to have a role in the workshops that we teach and other things that ACM does. It's a way to get to know the other officers in ACM and become an officer yourself sometime later. You can apply to become an intern for ICPC and other committees as well. So the form for that is linked on the slides, and make sure to fill that out by tomorrow if you want to apply. In addition, if you haven't already done this, you should join the Discord forum for this workshop. The Discord forum is useful if you want to talk to the officers to discuss some problems that you've been solving, some solutions that you're having trouble with. And other than that, it's just a great way to make friends, other people that are going to this workshop and also friends with the officers. And since we're not in person, the Discord forum is really useful because since we're online, you're really missing out on being able to talk to other people in the workshop. And we're really happy that the Discord is really active. So you can meet other people through Discord. The link to the Discord is also on the slides, so make sure to join that. And if you weren't here last time, you should create a Caddis account. Caddis is what we use for all the problems in all of the workshops that we do. So you can create an Caddis account and make sure to fill out the form. And this form is basically just for us so that we can keep track of your Caddis usernames and send you invites to competitions. So last time's workshop was about math, and we talked about modulo and modulo properties and some problems on that. And today we might not be focusing as much on math, but we will be using IO. And that's because IO is used for every contest problem. And we encourage you to use your own IO, considering that we went over IO in some detail last time. But still, IO templates will be provided for all of the problems that we have in and after workshop for all the problems. And those templates will be in the GitHub repository, and I will be linked in the slides as well. Okay, so for today, we'll be talking about arrays, and specifically the vector class in C++. We'll be talking about how to initialize vectors, functions that you can use to manipulate vectors, and how to iterate through them. Then we'll be doing 2 problems using 1D vectors, and then talk about how we can create 2D arrays using vectors. Tony will be going over this section, and he'll also guide you through a problem using 2D arrays. And finally, we'll have the contest for today. Okay, so arrays. So arrays are basically just an implementation of a list, and they are considered the most basic data structure. For example, if you were given a list in a contest problem and you needed to read that in, your first instinct would be to read that list into an array. Arrays are basically a bunch of elements that are stored contiguously in memory, and contiguously just means one after another. So for example, if we had an array of strings, those strings would be stored one after another. And what that provides is really fast access, because let's say you want to access the element at index 1, you could just say that you want to access that element and you would get that in a really fast time, in constant time, which means that it's independent of the size of the vector. So for that reason, vectors are useful for accesses and writes. Something to keep in mind is that all vectors are 0 indexed. And what that means is that the first element of the array is referred to by index 0. So for example, if you wanted to refer to dog, you would say array at index 0 is the string dog. And similarly, if you wanted like third object in the array, you would have to refer to it by index 2. So I've been using vectors and arrays interchangeably, but the data structure is called arrays, and in C++, the vector class handles arrays. And the use of the vector class is just that it provides some additional functionality over standard arrays. And this is just useful because you don't have to keep track of certain things that you would have to do by hand. The class handles that for you. An example of this is size. So the vector class keeps track of your array's size, whereas if you implemented arrays by yourself, you would have to keep track of the size by yourself. And that can be really annoying because if you have like multiple arrays, you would have to have like variables for each of them. And in addition to just size, the vector class gives us other functionality, but internally they're the same. So here's an example of how you would initialize a vector. You would say the word vector, and then in angle brackets, you would put the type. And this is the type for all the elements in the vector. So this would be a vector of integers. And then you put the name of the vector. I just called this vec1. And using this syntax, you just created a vector of size 0, which means that it has no elements in it currently. If you wanted to initialize a vector to a certain size, you could follow the same syntax and at the end in parentheses, put n, which is the size of the vector. Something to keep in mind here is that this size is like the number of elements starting from 1. So for example, if you said n was 5, you're creating a vector with 5 elements, and the valid indexes for that vector would be 0 through 4. Something to keep in mind though is that if you just specify a size, you're not specifying like what values you want to initialize each element to. So if you just use this syntax, you would have like random values in the vector. So if you want to specify like a certain value to initialize each element to, you could use this second syntax, which is just adding a second parameter. So this, by adding a 0 at the end, we created a vector of size n filled with all zeros. Okay, so iterating through vectors. So iterating just means going through the elements of a vector in order. So the standard syntax for doing so is using square brackets, which is using regular array syntax. So how you would do this is by using a for loop and use some variable to keep track of the index starting from 0. And you keep going until you're less than the size of the vector. And this ensures that you stay within the limits of the vector, because if you have a vector of size n, this would create, this would make I go from 0 to n minus 1, and those are all valid indexes. And to access a certain element of the vector, you would put your variable inside square brackets. So this is basically just the index, and this vector at I would return the element at I. So this is like the standard way that you would do it. Another way you could do it is by using iterators. And this is this second syntax right here. And on the surface, it looks like way more complicated, but iterators are basically just objects that refer to a specific element in a vector. So the way you would start is by initializing some variable to vec.begin. And vec.begin just gives you an iterator to the first element. And then you could do it++. And what that does is just increases the iterator one by one. And you do that until you reach vec.end. So in general, this syntax looks way more complicated compared to the first, but actually iterators simplify the use of iterating through a vector in some cases if you use this syntax. So by using this syntax, you can refer to each element in the array just by the variable element, and you don't have to use an additional variable. So basically, iterators enable you to use this second syntax. Some other operations you can do with vectors is pushback. And this is actually used very often. What pushback does is that it adds an element to the end of a vector and at the same time increases the size of the vector by 1. So for example, if you had a vector of size 5 and you did pushback 3, what that would do is create a new vector of size 6 and add 3 at the end. And this happens really fast. This happens in constant time, which we call O of 1 time. And we'll go over what O of 1 means more in detail, but you can basically add an element to the end really fast. Yeah, some questions in the chat were about, from the previous slide, about what the star means. And you don't have to worry too much about it. You will probably learn it in your classes soon. But what it means is, since IT refers to a specific place in the vector, to get the actual element there, you would have to use this star operator. But in general, if you stick to either this approach for iterating or this one, you won't have to deal with that. Some other operations you can do with vectors is deleting or inserting. But in general, you want to avoid using these functions. So, and the reason for that is because since the elements in a vector are stored contiguously, if you try to delete something in the middle, in order to keep the vector, keep the elements of the vector one after another, you would have to shift parts of the array back or forward in insertion or deletion. So in general, you want to avoid using them. And if you find yourself using them, you should probably use some other data structure because it's just extremely slow in a contest scenario. Some disclaimers before we start getting into problems is that a lot of problems that you think you have to use arrays in can actually not be solved by arrays in time. You would have to use some other data structure, such as sets or hash maps. And another thing about array problems is that they're ad hoc, which means that there's no particular technique to solve all of them. But as you practice and find certain types of problems, you can kind of advance and get better at solving array problems. So with that, let's try our first problem for today. You can find that in the example contest we have for today. It's called greedily increasing. We'll give you guys some time to get started on your solution and try to code that. Questions later. So let's go over the solution to this problem. And if you have any questions later about your specific solution, you can ask one of the officers in breakout rooms after the workshop. But for this problem, we have to find a set of elements that are each bigger than all the elements to their left. And like the wording of the problem statement can sound really confusing, but by looking at the sample input and output, it becomes more clear what we have to do. So for example, if we look at the first sample input, we have to find a set of elements that are each bigger than all the elements to their left. So if we consider the first element, which is 2, there are no elements before it, so we must include it in the solution. And then if we consider 3, well, 3 is bigger than 2, which is the only element to its left, so it's included here. But The next element, 1, is not included because 3, which is to its left, is bigger than it. So 1 is not included here. 5 is included because it's bigger than all the numbers here. 4 is not for the same reason. And then 7 is included because the largest element on the left is 5, and 5 is smaller than 7, and then 6 is not included. So one way we could solve this problem is by keeping track of what the maximum value to the left of each element. So how we can do that is by having a variable which keeps track of the maximum value to the left of the current value, and by comparing each value to that variable and then moving on to the next one. So how that would actually look is, for example, if we want to consider 1, we would compare 1 to the previous maximum, which is 3, and we would not include it in the solution. But if we were to compare 5 to the previous max, which is 3, we can compare that, include 5, and make 5 our new max. So in code, how that would look is that we, one sec. Yeah, we iterate through the array, and if the value that we're considering is greater than the previous max value, we add it to our solution array. So in our code, how we can do that is by initializing a vector GIS for greedily increasing subsequence, and this will be our solution vector. And we can also initialize another variable which keeps track of the previous maximum. We can initialize that to 0. And then we iterate through the vector using the first type of syntax that we talked about. And then we compare the current element at I to previous max. And if it's bigger, then we add it to GIS using the pushback function. And then we update previous max to the current. So this solution that we talked about is called a greedy solution. And that's because at each step, we make the locally optimal choice. So at each step, we just compare it to the previous element, the previous max, and if it's bigger, we include it in the solution. So a greedy solution is where you make the locally optimal choice at each step, and that creates the overall optimal solution. So greedy solutions are usually simple and intuitive to code, and for that reason, you should look for greedy solutions first. You can save yourself a lot of time, but you should also know that greedy solutions are not always correct. So you should make sure that your solution works for all the cases that they might test you on. Our second problem for today is disastrous downtime. Hopefully you find it more interesting than the previous problem. I think it is. We'll give you some time to solve this one, or at least get started on your solution. So let's go over the solution for problem B now. Okay, so in this problem, we're told that we have a number of servers and that each server can handle k requests in a second. In addition, we're given n requests, and we're given the times at which each request is made. All these times are given to us in milliseconds. And the question that the problem statement asks us is, how many servers do we need at minimum to successfully handle all the requests? So for example, if in a second we have 10 requests, and we have a k equal to 3, then we know that we need 4 servers to handle the number of requests, because the first 3 servers can handle 3 requests each, and the fourth one can handle the last request. So if we know the number 10, and we also know the number 3, then we can find out the correct answer. So we know k because it's given to us by the problem, but to find that number 10, which is the number of requests in a second, that's like the heart of the problem. So we want to find the maximum number of requests in a second, and then using that, we can find the number of servers that we need. So to find the maximum number of requests in a second, one of the first approaches that came to my mind was to make a counter that keeps track of the requests in a second. And then using each of the times that's given to us as a starting time, we scan 1000 milliseconds ahead and count the number of requests that we see. So how that would look is, for example, if we use 0 as our starting time, we would scan the rest of this array for times that are within 1000 milliseconds of the start time. So if we scan, we see that 1000 is not less than 1000, like it's more than 1000 away from 0. We want strictly less than 1000 milliseconds away. So if we use 0 as our starting time, there would only be one request in that second. Similarly, if we use 1000 as our starting time, we would scan through the array. The first thing we would see is 1010 milliseconds, and that would be in the same second as this, because 1010 minus 1000 is 10, which is less than 1000. Similarly, for the next one, we would do 1050 minus 1000, and that's in the same second. It's only 50 milliseconds away. And then we would continue to do the same thing with 2000. However, 2000 minus 1000 is equal to 1000, so it wouldn't be in the same second, so we would end here. And we know that all of these requests are made in the same second. So we can keep doing this for each second and update our counter if the requests in the current second is higher. So if we started from 0, that counter would be set to 1. And then once we test this one, we would set that counter to 3. For the next one, once we check starting time 1010, we would not change the counter because it's also 3. And we would continue this process for every single second, every single starting time. And at the end, our counter would be the max number of requests in a second, and we can divide that counter by k to get our answer. And this approach seems like it works, and in theory, it is correct. However, in a contest scenario, you might get this message, which means that your program was a little bit too slow. And so let's see why that would be the case. So in the problem statement, they tell us that we have n requests, and n at maximum is 10 to the 5. And if we assume that there are m requests in a second, which is the amount of requests that we would have to scan through, we know that m can be at max n, which means that m can be 10 to the 5. And so if for every request we're scanning 10 to the 5 ahead, we would have 10 to the 10 operations. And as a general rule, we should know that like in a computer in a contest scenario can only do 10 to the 8 operations per second. And so what that means is that our program will time out. Our program might be too slow. So if we go back to our approach and if we try to see if we're doing like some extra computations, and if we try to get rid of that, we can make our solution faster. So if we look at our method of counting, for example, if we're starting at 1000, we start scanning from 1000 and going to the right until we hit 2000, which is too far ahead. And that's when we conclude that all of the previous ones are in this second starting at 1000. Next, when we move on to 1010, we start scanning right here. And we continue until we reach 2000, and then continue from there. However, we should know that if 1050, for example, was included in the previous second, it would also be included in the next one. And that's because since these times are in sorted order, we know that 1050 comes after 1010. And also, since it's included in the previous second, it must be within the next second, because this is equal to or greater. So basically what that means is that this red part is extra. We're doing that computation again. So if we just start counting from 2000 instead, we would avoid having to check that overlap. So the way we can do that is by keeping track of the end of the previous second. So if we keep track of the end of the previous one, which was 2000 in this case, once we start checking for 2010, we can just start counting from 2000 instead of having to check from the beginning. So to do that, we can use a second variable called j to keep track of the previous second's end. And then once we want to consider a new start time, we only start incrementing from the end of the previous one. So we only start incrementing from where j left off. So if we have two variables, I and j, how we would use j is we increment j until we reach a time that is 1,000 or more than 1,000 away. So we would increment j by 1 and check if it's within 1,000. It is within 1,000 here. So then we increment j again. Again, it is within 1,000 of the start time. So then we increment j once more until we get to a point where it's equal to or greater than 1,000, and we stop. Then, when we consider the next starting time, we can start off where we left off, which was at 2,000. And then we can increase j from there. We increment j to 2001, and since that's within 1,000, we can continue incrementing from there. And so this approach will work in time. And before we talk about how fast this would be, let's look at the exact code for how we would implement this. So the way to do this is to initialize two variables, I and j, both initialized to 0, which is the starting index. And then what we do is make a loop for I starting at 0 less than n. And I is the starting time that we consider for each second. And then what we do is use a while loop in our for loop, which will increment j. And we continue incrementing j until until the starting time, the end time minus the start time is less than 1,000. So we keep incrementing j while this condition is true. And another condition that you want to check for is to make sure that j doesn't go out of the bounds of your array. So I just included an additional condition to make sure j is less than n. And once you get to a point where j can increase no more, you just update this variable m, which keeps track of the maximum requests in a second. And through this code, you will have checked every second, and m will have the value of the maximum requests in a second. And then using m and k, we can find the maximum number of servers required. So how much faster is this approach? In each step, we either increase I or increase j. And so what that means is that the number of steps that we do overall is proportional to n. And this can sound like a little bit complicated for now, but what this means, usually in programming, we only care about the order or what it is proportional to. In the previous example, we would call that O of n squared, and this one we would call O of n. which basically means that the number of steps required to solve this problem is proportional to n. We will go over this more in depth in next session, in Tony's session, but what you need to know is that this will run in time and that the number of operations in a second should be less than 10 to the 8. If you have any questions about that, please ask in the chat. Some things to know about array problems is that they are ad hoc problems, so there's no one technique. This previous one that we solved uses a two-pointer technique, and even in two-pointers, there is like multiple subcategories, and like to get better at them, all you have to do is practice. Some common array uses are in geography problems, or in to store permutations or generate permutations. Arrays can be used for schedules, for time series, and to implement other data structures such as heaps or binary search trees, or even like hash maps. Okay, so let's talk about 2D vectors, and Tony can take over from here. Tony, yeah, okay, cool.
Okay. Hello, everyone. Can people hear me? Okay. Sorry, I don't have a fancy background today because I'm still setting up my PC. And so I'm going to talk about 2D vectors today. 2D vectors are basically better vectors. No, just kidding. 2D vectors are basically just vector of vectors. If we take a look at the code on the right, we can declare a 2D vector like this. Essentially, we're just putting a vector of integers inside another vector. This way, you would have a lot of vectors stored inside one single data structure. It's really easy for organizing code, and it has a lot of really useful cases. And to access the numbers in a 2D vector, you just do vec square bracket row and then column. One way to think of a 2D vector is to think of it as a matrix. You have n rows and then n columns. You can index the integers inside the matrix by using the row number first and then the column number first, the column number second. Yeah, one thing to notice, to remember is that 2D vectors also follow the zero indexing law, which means the first row is 0. The first column is also 0. And here's just another way. Let me change it to the pointer. Yeah, here's a way to declare a 2D vector filled with zeros. Essentially, we're declaring a vector of n elements, and each of the elements in this n element vector will be a vector of m elements. And then we make each element 0. So this would give us an n by m vector filled with zeros. And the following one is basically doing the same thing, except it uses a function called resize. Oh, resize. For most of the times, I think just the top 2 usages would be enough. Now let's see a few examples. So in this 2D vector or in this matrix, what's the indices of number 4 colored in orange here? What's the indices of 48 colored in yellow here? And what's matrix 1, 3? What's matrix 2, 5? See if you can figure them out. Let's launch a poll. Okay, I'm gonna continue now. So first, let's solve the first question. What's the index of 4? The 4 is in the first row, the second column, and since in arrays or vectors we use 0 indexing, so it would be 0, 1. And then for the 48, it's basically the same idea. It would be 3, 2. And then with matrix 1, 3, 1, 3, we would go to the second row, the fourth column, which gives us 3. And finally, matrix 2, 5, if we go to the third row, and then we need to go to the sixth column. Notice that it's 5 here, and we need to add 1 to it. It goes out of bound. And this is bad, but it doesn't necessarily crash your program. So this is because of the implementation of C++ vectors and arrays. You will learn more about this in CS31. Now, with array syntax cleared out of the way, we can take a look at an example problem. It's called flowshop. It's the problem C on the contest, and then you can also see the problem using these 2 links. I'll give you guys 7 minutes to take a look at this problem. Just be warned that this problem is really hard, and it's totally fine to not have an idea of how to solve it. And I'll go through this problem step by step and try to make it as clear as possible. Okay, so this question is pretty hard to understand. It took me a while to understand what it's saying as well. Basically, let's take a look at the simple inputs. It gives us, in the first line, it gives us 2 numbers. The first one tells us how many swathers there are. And then the second integer tells us how many stages these swathers need to go through. And then following up, we have 2 lines of integers. The first line tells us, okay, so the first swather, it takes 1 minute to process the first swather in stage 1. And then it takes 2 minutes to process the swather in stage 2. And then 3 minutes in stage 3. Similarly to the previous line, it takes 3 minutes to process the second swather in stage 1. It takes 2 minutes to process the second swather in stage 2, and 1 minute in stage 3. And the goal of this problem is to find out when will these swathers, each of these swathers, be processed, right? So let's say we have 2 swathers. The first one goes into stage 1. It takes 1 minute to process it, and then it goes to stage 2. After 2 minutes, it goes to stage 3. And then after stage 3, it's finished, right? So that takes 6 minutes. And similarly, if we don't consider the first swather, if we only have 1 swather, the second swather, and then it goes from stage 1 to stage 2, and then to stage 3, that would also take 6 minutes. However, there's a catch. In each stage, there's only 1 worker. So that worker has to process its current swather before moving on to the next swather. So in this sample example, sample input, in one stage, the second swather actually has to wait for 1 extra minute before it can get processed. And that's where the 7 comes from. If you are still not sure what the question is asking, I have some better illustrations later. Okay, there's a question in the chat. So why does it have to wait the extra 1 minute and not 6? Is it 1 worker per stage 1 of every different swather? Oh, okay. So we have one worker at each stage. So this worker, after working on this swather in stage 1, so we have one worker in stage 1, one worker in stage 2, and then one worker in stage 3. So the worker in stage 1, after working on swather 1, can move straight to swather 2 without having to wait for the first swather to finish. So in this example, the first worker, it takes the first worker 1 minute to process the first swather, and then immediately after that, this worker can move on to process the second swather, even though the first swather is still getting processed in stage 2. The first worker doesn't care because that's not his job. So yeah, I have more examples later on coming up. And okay, well, there's one more question. So a worker only cares about its column. Yes, exactly. Yeah, so I have an illustration here. Let's take a look. We have 3 swathers in stage 1, and then the worker works on the first swather first, and then it pops the first swather to stage 2. And then the worker in stage 1 can move on to the second swather in this stage, while the first swather is being processed in stage 2. So after that, he can pop that swather to stage 2 and then start working on the third swather. Notice that the swathers are being processed in the exact same order as they come in, as they're numbered. Like right here, the first swather is processed, and then the second one, and then the third one. So that means that means the swathers also arrive at each of the stages in the same order, right? If we go back here, if you look at stage 2, the first swather comes in first, and then the second one, and then the third one, which means for the worker in stage 2, the order is also the same. The worker is also gonna work on the first swather, and then the second one, and then the third one. Which means for this question, the order is the same for all stages. And we can simplify this problem to only one stage. And then we consider one stage at a time. Eventually, we'll come to this third stage. And the finish time of the third stage would be our final answer. Now, to actually solve this problem, I made this diagram down below, and I'm gonna explain everything. Here on the left, the process timetable, we have 6 slots, right? This is sample input 1, by the way. We have 6 slots. This is the time it takes to process the first swather in stage 1, the time it takes to process the first swather in stage 2, and the time it takes to process the first swather in stage 3, and so on and so forth. Right on the right side, we have stage 1 with 2 swathers. Stage 2, initially, there's no swathers in stage 2 or stage 3, so they are empty. And then let's take a look at the ready time. Right here, we have 2 slots, 2 integer slots, right? I'll use them to represent the time, the ready time of each swather. So for example, if this swather is being processed in stage 1, right? If it's time 0, and then the swather is starting to get processed at time 0, and if it takes 1 minute to process this swather, then the ready time of this swather would be 1, and that's the time at which this swather is ready for the next stage. Similarly, on the top, that's the ready time of each of the workers. So for example, if it's time 0 right now, and then worker 1 starts working on the first swather, it will take him 1 minute, right? So the ready time of the first worker, I would set it to 1. And that means we can't, the first worker can't start working on the second swatter until time 1. I'll give you like a few seconds, no, maybe half a minute to process this. And if you have any questions, if anything's unclear, feel free to ask in the chat. If not, I'll move on to the next step. There's a question in the chat that says, so is it only ever stage 1 that has a backup and causes workers to wait? What do you mean by causing workers to wait? Because the workers, unless there's no more swatters to be processed, the workers, oh, is that my phone? Sorry, one sec. I need to. Sorry about that. Like has, oh, okay, has to wait for the previous swatters stage 1 to be done. Oh yes, yes. So before stage 1, before any swatters in stage 2, the worker in stage 2 can't work on anything. So the worker in stage 2 has to wait for something. The swatters have to go through the stages in order. So like while the first worker is working on the first swatter, the second worker and the third worker don't really have a job to do, which is sad. So the first worker gotta work hard. Okay, let's go to the next slide. And let's look at stage 1 first. Stage 1 and the first swatter. It takes 1 minute to process a swatter. So, which means the next time this swatter is ready would be 1, right? And then it takes 1 minute for the worker to work on it as well. So we set the ready time of the worker to 1. And after processing the first swatter, we pop it to stage 2. Now, the worker is ready for the second swatter. And it takes 3 minutes to process the second swatter. And notice that the swatter is ready, it's already ready, right? It's ready at time 0, which means, and currently after working on the first swatter, it's time 1. So the second swatter is ready. And to calculate the ready time for this second swatter, we add 3 to these two numbers and then find the larger one, right? Both the worker and the swatter have to be ready before the process can begin. And that's why we have swatter ready time equals max of worker ready time and swatter ready time. Once both of them are ready, we can start processing it. Add the swatter process time to it, and then that gives us the swatter ready time for the next iteration. And then we just set worker ready time to the swatter ready time because they finish at the same time. So in this case, it would be 3 plus 1, which gives us 4. Now, the first worker has done his job, so he can retire now. We are on stage 2, and we have the ready time for each of the swatters. We have the ready time for the worker. Notice that this is very similar to the situation where we are in before we start stage 1, right? So we can just throw away stage 1. We look at stage 2. Currently, the worker has to start with the swatter with the lowest label number, which is the first swatter. It takes 2 minutes to process the swatter in this stage. And the swatter is ready at time 1. The worker is ready at time 0. we need to take the max of these two, because both of them have to be ready for the process to begin. So we take the max, which is 1, and then we add it to the process time to get the new swatter ready time. And once we calculate that, it would be 3 in this case, which is 2 plus 1. And we save that number in the swatter ready time slot and also the worker ready time slot. And then we move the swatter to stage 3. Similarly, we do the same thing for swatter number 2. The ready time for the swatter is 4. The ready time for the worker is 3. So we need to wait until the swatter is ready before this worker can start working on it. And that is time 4. And then we add the process time to it, 2 plus 4, which gives us 6, which means both the worker ready time and the swatter ready time are 6 now. Now, both of these swatters are out of stage 2. We don't have to worry about it anymore. We move on to stage 3. It's the same thing. The swatter's ready at time 3, the worker's ready at time 0. So we take the max of the two, which is 3. We add it to the process time, which gives us 6. Similarly for swatter 2, the worker's ready at time 6. The swatter's ready at time 6. So we add 1 to both of them, and that gives us 1 plus 6 equals 7. And notice that both swatters are through stage 3, which means we're done. And look on the left side here, the ready time of the 2 swatters is exactly what we want. And that's the time the question is asking for. This is pretty complicated. So if you have any questions, is this clear to everyone? Does anyone have any question? There's a question that asks, would this be considered recursive? No, actually, we can solve this problem without using recursion. And it actually isn't that hard to solve it without recursion. Recursion is pretty complicated. So we're gonna avoid using it for now before you guys have learned it in CS31. And also, I think you can write every single recursive program using loops if you want. Maybe sometimes it's hard, but it's possible. Okay. If nobody has any questions, I'm gonna move on. Oh yeah, we're done. Yay. Here's the implementation of this program. It only uses loops. There's no recursion here. I'm just gonna go through the lines to explain what I do. In the first line, we write vector int t process, blah, 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 blah. This is basically declaring a 2D vector to store the process times. And then we take the input, we store all the process time in this 2D vector. And then we declare 2 other vectors, t swatter ready and t worker ready. So t swatter ready is a vector of n elements, each indicating the ready time for that swatter, right? We have n swatters, so we need n slots to store these ready times. Similarly, we have a vector of n elements, and it's called t worker ready, which is used to indicate the ready time of each worker. All right, and then we start, let's look at this nested for loop. The outer loop loops through the stages, just like what we did earlier. We looked at stage 1 first, and then stage 2, and then stage 3. So we looped through the stages using the outer loop. And then the inner loop loops through the swathers. And then we set T swather ready I, which is the index of the swather. So the ith swather is ready when both the swather, when the swather is already ready for this stage, and the worker is already ready, right? So that's T swather ready I, and then the worker ready time is T worker ready J. J is the stage number. And then we add that to the processing time. We get the new swather ready time. And then we set the worker ready time to be the same as the swather ready time. This is basically what we do for each swather. And then we repeat in this inner loop, we repeat that for each swather. And then on in the outer loop, basically just repeats each stage, iterates over the stages. And after this nested loop, we, just like what we did on the last slide, we got the final answer. We just need to print out the output, and that's it. Yeah. Is this clear to everyone? Feel free to ask in the chat.
Can I ask a question?
Yes.
If we declare that, those vectors ready, for instance.
Yeah.
When we start running through the loop like once, like to access the first value at T worker ready, would it necessarily be 0?
Oh, yeah. So this is that's what the syntax means. Yeah, I should clarify that. So for each of these vectors, we set them to 0. That's the second, what the second parameter means.
For some reason, I thought that was a 2-dimensional vector. No.
Oh, yeah, yeah. We only used one 2D vector here to store the processing time. That's a good question, though. Yeah. It's sometimes you don't realize that you initialize all the, like whether or not you have initialized your array to 0, and that can cause some really nasty bugs. But in this case, yes, we initialized both arrays, actually all vectors to 0. So that would be fine. Okay. So that's it for the example problems. And if you have any questions, comments, or concerns, please tell us in this feedback form. We really appreciate your feedbacks. And I'll give everyone like 2 minutes to fill it in. And we'll start our contest after that.